We present a power-aware emulation environment for long-endurance solar UAVs. To provide some background, power consumption on UAVs is split between the aircraft systems, including the propulsion system, flight actuators, and the flight avionics, and mission components, including the computational unit and sensors. Our motivation is to maximize mission outcome and endurance for a solar UAV. In order to do so, we need to perform power-aware path planning to optimize power consumption. A high-level path planner algorithm needs a power model that allows it to evaluate and optimize the trajectory. Therefore, we created a power model that uses specific data such as velocity, climb rate, etc. to calculate the expected power consumption. To be able to test these path planning algorithms and other future autopilot features, we developed a power-aware emulation environment that allows rapid prototyping of embedded soft and hardware. In an electric airplane, the battery and later on solar panels provide electric propulsion power. The motor converts the electric propulsion power into rotary power to drive the propeller, which itself converts into rotational to thrust, applying a forward force to the airplane. To calculate the propulsion power, we need to calculate P thrust and the motor and propeller efficiencies based on the state of the aircraft. Then we can invert the diagram to calculate P propulsion. The power model uses analytical models to calculate P thrust and experimental data to calculate the efficiencies. We created an emulation environment that allows to rapidly test and evaluate autopilot embedded hardware development. In the emulation environment, the same embedded hardware that is used to control the aircraft and gather data from the mission and flight sensors is connected to a simulation environment. The interface of this connection emulates the interface to the sensors and actuators, making the embedded hardware oblivious to if it is running on the real world or in the simulator. The simulator itself can be modified and extended to simulate desired scenarios that need to be tested. Addition to the simulation can be used to integrate power models, as described earlier, failure scenarios, and much more. The integration of the power model into the emulation environment was experimentally validated using a fixed-wing UAV testbed. The video shows the ground station with simulated video from the simulator in the top left. The top right provides an overhead map with a yellow aircraft icon, planned waypoints in light blue, planned trajectory in yellow, and actual simulated trajectory in white. The bottom right has a primary flight display and sensor data output from the simulator. The bottom left has a display and tuning interface for the PIDs used in the autopilot. It should be noted that the pitch oscillations seen are due to the differences between the real and simulated aircraft, and that the same tuning parameters are used. A 3D comparison of the flight path shows that the experimental flight path in red and a simulated flight path in green. The aircraft is plotted at 6 times scale and every 2 seconds. There is an excellent correlation with the only notable deviation seen in the bottom right corner, which is likely due to wind. Comparing power consumption, we see excellent correlation. The red is power measured on the real aircraft. The blue is an estimate for power consumption using the aforementioned power model and the measured inertial sensor data. Finally, the green is an estimate for power consumption using the power model and the simulated inertial sensor data as seen in the video. The peak in the green curve is a result of the pitch oscillation in the beginning of the climb. To conclude, we have developed a power model that includes both the propulsion system and mission avionics and is solely based on the aircraft inertial state. Additionally, we have created an emulation environment for use as a tool for rapid prototyping in research and education, and we have integrated the aforementioned power model into the emulation environment. For future work, we plan to extend and refine the power models, integrate a solar model, develop power-aware path planning and control, and perform long-endurance solar-powered flight.